I know. Yeah, I'm moving over here. So an announcement. Well, two things I want to mention under the handouts. If you've printed the things that need to be memorized, it was a hello. If you've printed this out, you want to reprint this because I posted it originally as a Word document and I didn't catch it, but it had cropped off the domain. So if you printed this out, you would have probably saw that or thought that the domain of the inverse sign was the range. So I did upload the PDF, so it should be fine now, but it did get cropped off. If you did print that out, you might want to reprint it or just take note. That's inaccurate as it was. The homework in MyMathLab, you might have. Do y'all have any questions or? Okay. The homework in MyMathLab, if you've done any of it, some of them have a -T next to the problem number. Not the official problem number, but remember this number here is 6.2, similar to question 3 in the textbook. Some of them do have a -T where it's meant for you to use technology on. So like graphing utilities or something to that effect. Since we can't use those things in class, questions with a -T are not likely candidates at all for the exam. Just a heads up, if you see the -T, use technology. I don't know if there's any yet, but I know there are a few throughout the assignments. That's all I had. Do y'all have any questions or issues? Homework questions? Yeah.
For the questions, just the ones being like the exam, are you gonna on exams ask conceptual questions like definitions, or is it mostly gonna be just working out problems?
No, there's not a whole lot of conceptual, if any. There might be questions that are, like I'm thinking about maybe the final, like what's the formula for arc length or something?
Yeah.
And you have like multiple choice.
Okay.
So those might show up on the final, but I wouldn't call them conceptual.
Okay.
There's so much mechanics that we have to get through that most of the exam is just displaying those mechanics. Yeah. Any other questions? Yeah.
Will your exams usually have a true false section on it?
No, because those would be conceptual.
Okay.
If there were, again, it would be more in line of, like, is this the correct formula for surface area or something like that? Yeah, it's a bit harder to ask conceptual questions in Calc 2. It's easy to do that in Calc 1, so yeah, not too many of those. Any other questions before we continue with 6.3? Okay, so where did we leave off? Okay, we left off talking about volume. How do we find the volume of a region that's bound by a curve or two curves? And particularly what we pointed out was that volume in general, if we look at the area extended along a length, we find the volume, right? Volume is 3 linear dimensions. Area times another linear gives us volume. So we have here the cross sections. Remember, those things are getting infinitesimally small. We're just kind of over exaggerating them right now. We find the area times the thickness, dy or dx, and then we sum all of that. We sum all of these pieces to give us that volume. And so the important thing that we left off with in 6.3 was, in order to find the volume, that we need to look at the integral of the area, function of x, or it could be a function of y if we're integrating with respect to y. But we've got an area function times the thickness, dx. So we've got our volume, and then we have our integral, which is an infinite sum.
Is it divided like
The derivative of volume. The derivative of volume is, we might could loosely say is area. It really would depend on the context. Because this, as we're looking at it, it's not really just an area function because we have that dx there. So it is a volume that we're summing up, really. I've heard other professors say that, the antiderivative of area is volume, or the antiderivative of volume is area, or derivative of this is that. I suppose we could look at it that way, but I would rather look at it as the sum of area times thickness gives us a total volume. Yeah. So the area function that we're talking about is the area of each cross-section. So the cross-section is either given to you or it depends on the shape. The two methods we look at in 6.3 and 6.4, we're going to see that the cross-sections do generate a specific figure, and then from that specific figure, we're able to determine what the volume generated when things like this here are revolved around the x-axis or the y-axis. But where we're starting with is just a general slicing method, because the methods in 6.3 and 6.4 are directly built off of this notion right here. Okay, so we find the area of the cross-section as a function of x or as a function of y. It just really depends on the setting. But again, the important thing is that it's the area of the cross-section, that function, capital A. All right, so here's our first example. Just the general slicing method utilized to find the volume of this figure to the right here. So we're going to use that method to find the volume of a solid with a circular base, radius 5. And whose cross-sections perpendicular to the base, parallel to the x-axis, are equilateral triangles. So at no point in this class do we think about the three-dimensional shape. We always translate it into 2D and think about the 2D situation. So even though we're finding the volume of this here, we want to translate that into its two-dimensional counterpart. Well, let me do this. So we already see the two-dimensional counterpart is a circle in the xy plane. So we have our circle, and just be mindful of the orientation as well. So the cross sections are parallel to the x-axis. So let's just say this is one of our cross sections right here. So that's the setting that we're working within. A couple of things to note, just like we noted in 6.2, it matters which direction your rectangles are running, vertically or horizontally. Right? This is top minus bottom. This is right minus left. This is everything in terms of y. This is everything in terms of x. So since our cross sections are parallel to the x-axis, they have thickness, that's dy. So really I recommend, maybe you have a different way to approach this, but I just recommend starting off that way. You've got to know what bounds we're dealing with, are they x or y, and you got to know if the function needs to be solved for x or does it need to be solved for y. So once we kind of have our bearings, then we think, what kind of figure is generated by our cross sections? Equilateral triangles. So it tells us that the cross sections are equilateral triangles. So again, we're thinking about this formula, and in order to find that volume, I first need to come up with the formula in terms of y for the area of those cross sections. So let's just write this out. Area of cross sections since they're equilateral triangles, the area of all of those are 1/2 the base times the height. Everybody okay with that? So really that's the first thing. What kind of figure am I dealing with? My cross sections. Write out the formula for the area. Everything needs to be in terms of y. So having a b and an h here isn't sufficient. We have to have the base and the height in terms of x. We're solving for x. Sorry, I said that wrong. In terms of y, meaning we're solving for x. Because it's our rectangles or our cross sections have a thickness dy. So let's note that we now need b and h as functions of y. In other words, we're thinking about finding some equation and solving for x. Excuse me. So this is where the boundary comes in. The boundary is the circle. One of the dimensions of the triangle we can find already. Which dimension of the triangle can we find? Yeah, the length of the base right here, right? So every one of our cross sections, what we're looking at is those. I put another cross section over here, and I'm looking at this equilateral triangle. So that length in red is the length of the base. Of course, the length of each base of the triangles varies. If I'm here, it's a different length than it is here. So as we go from the bottom to the top of the circle, the lengths of each triangle are varying. So we have to use the circle to describe that as an equation or as a function. Yeah?
Would you just use the radius then multiplied by pi, or
Yeah, so what do you mean? What would that look like?
the area function of this? But would you multiply? Would you use the radius times 2 though? Start at the origin.
Times 2, yeah. So you're thinking about the radius of the circle here, and we've got 2 of them, is measuring the length of that. Yeah.
Like did you
Yeah.
start at the origin?
Or 2x. Sorry?
Did you start at the origin like along x and y?
Along x and y? Well, you've got to think about which way your cross sections are running like this. So this would be this is how we would measure that radius right here, from here to here. Or you've got two of them.
I know what you're saying.
So we can think about let me see if this makes sense. If we label this as the base, and since we've got a horizontal element, we're measuring the length of that like we did in 6.1 or 6.2 rather. It's just the right minus the left. So the base is the right minus the left. Or since it's symmetric with respect to the origin, we could just say it's half of that. It's half of the length. Or sorry, half of the length would be the right minus 0. But then we would have to double that. So I guess there's a couple of ways you can think about how we're measuring the length of that base. Does that help, Trey, or was that what you were getting
I
at?
think what he was trying to describe is that you could form the points from the middle of the centermost point and have that be a radius or diameter rather, and it would still fulfill all of your points across. It would just be a little bit easier to look at or determine that diameter. Is that what you were getting at?
Yeah, exactly.
Do you understand what I'm saying?
Not really.
I think it's relevant.
Can you like draw? Would you mind drawing it out or like?
Sure.
Because yeah, I'm having a hard time.
Wouldn't that only be true if it was going to the origin?
I'm not quite-
So then you
I'm not-
wouldn't be able to find the volume for the other ones. That's the issue.
I see what you mean.
Did you hear? So,
Yeah, so-
right, it would only
Yeah,
be
I'm sorry.
if you go to the
What
origin,
he's saying
that's the
though
only
is
reason why
instead
you
of
can
going
use the
across
radius.
this way, you
Otherwise,
Okay.
it's gonna
cross through the
increase
origin
the
to
edges
a
to the
point
edges.
here,
Uh-huh.
hence all of those sliced this way.
Oh,
But then
yeah, okay.
what you're saying is that you wouldn't have a thickness
Like
of
if
dy
when you right when you move to the
a
edge, you wouldn't be
consistent
able to use the
thickness.
5 for the
Okay.
radius.
Yeah, so yeah, we wouldn't want to go through we wouldn't want to just slice through the origin, because if we did, that's fine for that piece, but we also have to slice this way and slice this way, right? First of all, it's violating what the problem tells us is happening, because all of the slices are made parallel to the x-axis. Second of all, it's not as easy to measure a length that's crooked like that. It's easy to measure a length that's horizontal or vertical because it's just the right value minus the left value. Here we would have to actually come up with the equation of the line and then measure the distance from those 2 points. So it'd be a lot more difficult. So yeah, through the origin, we're always talking about the diameter of the circle, but now any other place throughout the origin that's not passing through the origin, now you're having to measure the length of a chord. So it's not as straightforward. You could certainly do it that way. It would just be very difficult. Yeah, sorry I didn't understand that.
Oh, no worries.
Thank you for the clarification too. All right, so the base of all of our triangles, everybody agree it's right minus the left, or it's twice the distance, right minus 0. So now we just need to come up with a function so we can measure the right side and the left side as a function. Okay, so we've got a circular base, radius 5. We're just going to write down the equation of the circle centered at the origin with a radius of 5. Again, we're looking at our cross-section's thickness dy, so this equation needs to be solved for in terms of y, meaning we've got to solve it for x. So our equation we're looking at is x equals to plus or minus the square root of 25 minus y squared. So the positive root indicates positive x values, the right half of the circle. The negative root is for negative x values, which is the left half of the circle. So I'm just going to go ahead and draw this out. This is, it's not going to be a great circle, but we'll try. Sorry, it's a bad circle. Pretend it's a circle. Okay, so those are the two we're looking at. We do want to look at it that way because we have to measure the distance from the right to the left. Yeah.
So then can we just say chop off the negative half and double it since it is circle and it's center on the origin, so you can deal with one side?
Right. Yeah. Yeah. So that's what we're doing here. We're looking at half of that, and then we've got to double it. Yeah. Either way, we still need one of the boundaries.
Might as well throw away the negative one.
Yeah. So now, when we look at this length, again, it's just the right minus the left, or we can just look at half of it and double. Right minus 0 times 2. Whichever one makes more sense to you. However we look at it, b is equal to what? David?
2 square root of 25 minus y squared.
Right. So that's the length of the base. Notice it's a function of y, which we needed because we have thickness dy. So there's the length of the base of each one of those triangles. Do y'all have any questions on that? And really that just depended on the boundary of the curve. But if we're still thinking in lines of how we kind of measured those things in 6.2, hopefully none of this stuff is too difficult. It can get pretty cumbersome as far as what you're dealing with, but the ideas that we're talking about are still the same. So there's the base in terms of y. So we've got that accounted for. Now we just need h as a function of y. So how can we get h as a function of y? So the height is coming out at us. So the equilateral triangle's apex is out here somewhere. So how do we measure that height?
If it's an equilateral triangle, wouldn't it be the same height as your cross-section circle?
Not quite. So it's close. The height of the equilateral triangle isn't the length of the base.
I was gonna say you should be able to use the rules to get square root of 3 times the base, or a 360 triangle.
Yeah. So in any equilateral triangle, square root of 3 is always involved when we're talking about the height versus its base. So if you don't remember that, let's just look at it. Here's our equilateral triangle. Just pretend. So we have all of the sides equal. And then here's our h. So really what we're looking at is we're looking at this triangle, where that's our h. This is b, and the base here is what? Yeah, it's half of b, because we just bisected this, perpendicular bisector here. That's b over 2.
H should be square root of 3 times b.
It's actually square root of 3 over 2 times b. So it's just Pythagorean theorem here, solve for h. Luckily for us, we already have the base in terms of y. So there's our... Do what?
Square root of 3. Where did that come from?
So this is... I'll erase this, but this is h squared plus b squared over 4 equals to b squared from the Pythagorean. And then we're solving for h, so we've got h squared, b squared minus b squared over 4. And so we have 3b squared over 4. That's h squared. So when we take the square root, we have the square root of 3. The square root of b squared is b, and the square root of 4 is 2. Does that make sense? So that's square root of 3 times the square root of b squared over the square root of 4 for h. Does that help?
Yeah.
Okay. So the height of any equilateral triangle is root 3 over 2 times its base. There's its base. Now we have also h as a function of y. Are there any questions on that? Yeah.
Can we cancel out those two?
Yeah.
Okay.
We'll cancel those 2's out. But just be really careful, because if you find the base, let's say like we found the base first and we went ahead and plugged it in here and we have 1/2 times the base, so the 1/2 and the 2 go away. Just be super careful once you get to this step that when you plug the base in, you're actually plugging in 2 root 25 minus y squared. don't plug back in here again just the root of 25 minus y squared, because that's not the actual length of the base. Okay, so there's our height in terms of y, as was mentioned. So we've got our height in terms of y as well. So then we go back to the area of the cross section. So the area of the cross section we had as 1/2 times the base. Oops. Times the base times the height. No, go away.
Put the Windows button in the corner, the bottom first.
Oh, thank you. Times the height. Yeah. Everybody okay with that? 1/2 base times the height. So we can simplify this. It actually turns out to be a lot nicer than what we have here, right? Because we can multiply the roots together, and this 2 and this 1/2 are gone. So the area of cross sections are given by root 3 times 25 minus y squared. Do y'all have questions on that?
Would that actually be volume of one?
Sorry?
Would that actually be volume of one? No, I think the integral is just there.
No, it's just the area. Because remember, this came from 1/2 the base times the height. The volume is obtained by when we put this in front of the integral, and then we tack on the dy, because the dy is the thickness of all of it. Yeah. So, excuse me. So we're just saying that if our equilateral triangle is here, the area of this thing, let's say we're talking about that one that's in blue, the area of that is the square root of 3 times whatever this y coordinate we're at. Maybe this y coordinate is positive 2. Then we have the area of that triangle is the square root of 25 minus 4 times the square root of 3. If we then move this up, maybe this thing here is at 3. The area of that equilateral triangle, root 3 times 25 minus 3 squared, and so forth. The volume is then when we look at the thickness of this thing. So like if we have this thickness here, that's our dy, this thickness. So then that gives us the volume of each one of those super, super, super thin triangles, and then we're just adding all of those up as we progress. So honestly, that's the vast majority of the work in these problems is constructing that area function. So then when we say the volume is the area function, let's just write that. Times thickness. And we sum all of that up. Where does y range from? Okay, so be careful. we're finding the volume of this whole thing, right? All of these equilateral triangles filling up this region. So it's going from -5 to 5. We can utilize symmetry, but we've got to be careful on how we write that. Say it again.
Because that was about that. So are you going to do -5 or are you going to like use symmetry?
Right. You could go either way. Honestly, what I would do is, since we can find the volume of this top half and then double it because it's symmetric, that's what I would work with, just so one of your lower bounds is easier. So that's just equivalent to saying twice the volume from 0 to 5. So whichever one you want to use, it doesn't matter. It's the same volume. Let me write that up here. Okay. Questions on where we're at? We're going to use that one. We're going to pull out our constants. Anti-differentiate 25 with respect to y gives us 25y. Antiderivative of minus y squared is y cubed minus y cubed over 3, evaluated from 0 to 5. So just the advantage of having one lower bound is 0. It's just easier to evaluate because when we plug all of that in, all of this is 0. 500 root 3 over 3 is the volume. Sorry. Okay. So questions on the setup here?
So those are identical?
Yeah, these two are the same.
They would yield the exact same.
Yeah, just because of symmetry. So this one here, we would just find the volume of that top half of the circle and then double it. So we can use the general slicing method rather to derive the volume for a sphere of radius capital R. We're going to slice parallel to the y-axis. Does anybody happen to remember the volume of a sphere? Yeah. So again, we don't want to think about the three-dimensional object. We want to think about the two-dimensional object. Again, this one. And we're told to slice parallel to the y-axis, just so we're not left wondering. So we're going to slice parallel to the y-axis. This time our slices we have a thickness in the x direction. So everything in terms of x. What's the equation of my circle that we're dealing with over there? Yeah, whatever r is, it's not given. And since our rectangles or our slices have a thickness x, we want to solve this equation for, we want it to be in terms of x, which means we need to solve for y, right? Yeah. And so this time positive y, top half of the circle, negative y is the bottom half of the circle. Double, yeah, so we could take, here it's top minus bottom, or we could say it's, since we're only talking about, I suppose we should back up a little bit before we answer that question. What are the cross sections that we're talking about or dealing with? Anytime I slice into the sphere, what cross sections do I generate?
Circles.
Circles. So all of our cross sections are circles. We're going to find that as pi r squared. Let me write this so we're corresponding in case you're confused. So these are coming from what we just drew out. Would we have a capital R there, or should we use a different R? Do what?
I said lowercase.
Lowercase. Why?
I just said because it's not a sphere, it's a circle.
Well, yeah, because it's, well, yeah. Is this radius of our sphere the same as the radius of this circle? Or the same as the radius of this circle? Right, now here's this radius, here's this radius. They all vary throughout this circle. They're not always fixed as capital R. Does everybody see that? Because think about the rest of the sphere. It's coming out at you and it's going back into the board. So then we can think about, all right, well, I just need this R in terms of y, or sorry, in terms of x solved for y. So once again, we're thinking about what's the top length of the top minus the bottom, but we don't even have to go that far because half this distance is always the radius, lowercase r, right? So lowercase r is found by doing what? Subtracting what from what? The top, not the top minus the bottom. Top minus 0, right? Because this right here is our radius. This is lowercase r. If you did top minus bottom, you would have to half that. So the radius is, let's write it out both ways, half the top minus the bottom, or it's just the top minus 0. So what is the top minus 0? What's the, how do we describe the top part? Yeah. So right over here again, area is pi times r. I'll just write that for a minute, minus 0 squared, right? Pi r squared. Because the top portion of our circle is the square root of r squared minus, let's just say capital R squared minus x squared. pi r squared. So this is now what we're using as our area function for x. Any questions at all? And that's in these problems, by far the hardest thing to do is set up the area of the cross sections. Everybody good? Okay. So then our volume is the sum of the area times the thickness. And then where does x range from to r, right? Negative r to r. Capital or lowercase? Capital, because we're generating the volume of this solid. Remember, this circle is x squared plus y squared equals capital R squared. So this is, if we need to label it, this point over here, r, this point over here, negative r, negative r, r. So those rectangles or circles, if you will, for x are filling up the region from negative r to r. Everybody okay with that? Yeah.
Can you still use symmetry there and go 0 to r?
Yeah.
I think that does happen.
Yeah, that's what we'll do. So that we've got, again, symmetry. So we don't have to go from negative r to r. We can go from 0 to r and then double that. But I do want to at least write this out as is.
You just pull it down.
Yeah, we'll pull out the two, both the 2 and the pi, because it's a constant. Just at least wanted to write that out according to our formula on the previous page, and then we can like take care of constants and stuff after the fact. Again, we'll just denote here, this is by symmetry. Remember, we're integrating this with respect to x, so we have our constant, 2 pi. What's the antiderivative of capital R squared with respect to x? R squared x, right? This is R squared x minus the antiderivative of x squared evaluated from 0 to capital R. Again, remember, these things are in terms of x. Our functions in terms of x, so are our bounds. The bounds, capital R, that's our x value, and 0, that's our x value. Does that look all right? Okay, so let's evaluate this. It's 2 pi times. So first, capital R in for x. This is now r cubed. And then we've got an r cubed over 3 minus r cubed over 3. So there's f of b minus f of a. That's just going to give us 0. 0 in for x, 0 in for x. So we get what we need to get. R cubed minus r cubed over 3. So we've got 3r cubed minus r cubed over 3. That's 2 pi times 2r cubed over 3. Multiply 2 pi times 2, so we have 4 pi r cubed over 3. Is that right? Yeah. There's our 4/3 times pi r cubed. honestly, the antiderivative stuff should be secondary. I do want to make sure everyone's okay with how we're getting the area functions before we move on. So please, if you have any questions, ask.
So is that kind of just technically the proof of why that's the volume of the sphere formula?
I mean, I guess we could consider that one proof for the volume of a sphere for sure. Because we didn't, I mean, that involved us not even dealing with a sphere, just using the general slicing principle to get a volume. So yeah, we could call that a proof.
I guess that has to create a circle that's like, given that, and you can almost say that one requires the other.
Yeah, yeah. Yeah, it's kind of philosophical. I like it. Yeah. And which came first, the circle or the sphere? I guess. Right. All right. What's funny, right, is the point has no dimension, but then a line consists of infinitely many points, right? So a line doesn't have a dimension. Then we extend the line out into a plane. The plane doesn't have any dimension, right? It's still made up of infinitely many things that don't exist. But then we take the plane and we extend it out and we sweep out like a prism. Now we have a three-dimensional object that exists, like this table. But it mathematically consists of points, lines, and planes, none of which exist. So out of all of that stuff that doesn't exist, we get something that exists, right? Like, so really, geometry is based on a paradox. You just have to accept some of these things, otherwise, it doesn't make sense. The guy who studied infinity, he came up with two types of infinity. There's countable and uncountable infinity. That dude went crazy, so don't think about this stuff too hard. Okay. Well, then that's where we'll end the general slicing method. Like I said, though, the principles there do carry over to kind of our first method for volumes via revolution or rotation. So the difference here is, in those previous two examples, we weren't rotating anything. Now what we're going to do is we're going to take a region such as R, bound by this function in the x-axis, A and B, and then we're going to revolve it around an axis to generate a solid. We're going to then compute the volume of the solid that's generated by revolving. Okay. So I know it says this specifically what the cross sections are, but let me note this first method, the disk method. It's really important that we understand that the disks are generated when the rectangles or slices, however you want to think about it, are perpendicular to the axis of revolution. So, for instance, we're taking this region here and we're going to revolve it around the x-axis. So let's revolve it around the x-axis. In 6.3, we're going to look at what happens when our rectangles or our slices are perpendicular to the axis of revolution. And then in 6.4, we're going to look at what happens when our rectangles or slices are parallel to the axis of revolution. So maybe you can visualize what they are. Here's so there's our, let's move that a little bit more. There's our cross section, our slice, or our rectangle, and then when we revolve that, notice it again, it's perpendicular to the axis of revolution, which is the x-axis. So we're revolving that around. That rectangle is turning into a what? A circle. So the cross sections that are generated here are circles. And so we take that pi r squared, we fit it back into the method we just did. We say, well, it's pi r squared. How do we determine the radius of that particular circle? Because we see they vary, right? This this is the radius for this circle that's rotated here, but the radius of this circle is much larger. We're rotating that circle here. So how do we measure the radius? This is our radius. Again, we've got a horizontal element. How do we measure that?
Would you do the 1/2 top minus bottom?
Well, would we need to do that here?
Or could you, since it's a function, could you integrate?
Yeah, right. We'll end up doing that for sure.
Your radius is just the function value at whatever x is.
Yeah, so the radius is determined by the function, right? Once again, we're faced with measuring something that's running this way. How do we do that? Top minus bottom. What were you going to say, Trey?
The radius is the area
No, because we're not finding the area of this. We're taking this whole thing and we're revolving it and finding the volume. The radius is determined by this x value, right? But that doesn't tell us. That tells us kind of where it is over here, but that doesn't tell us, how big the radius is. Is it this, or is it this, or is it this, right? That variation is determined by the function itself. Right. So this again is just top minus bottom. Is our radius, but we're butted up against one of the axes, so really the bottom function here is always 0. The radius is the top minus 0. The top is varying depending upon the function value. So the radius is just the distance from f of x to 0, f of x minus 0. So that's what we see here in this formula. Sorry if you can't see it very well. It's kind of small. But volume integrates from a to b pi times f of x squared dx. So since all of the cross sections are making circles when we revolve them around the x-axis, that's our pi r squared, area of the cross section, pi r squared. Does that make sense? And then, of course, we've got to take all of those circles that are generated from here all the way to here and sum all of that up.
So you could multiply by 2 somewhere, right now.
What would you multiply by 2?
900.
Yeah. Everybody all right with what we're doing here? So this is the disk method. We're calling the filled-in circle a disk. And then times the thickness gives us the volume of that disk. And then we sum from A to B. So that's going to give us this entire volume, which is this figure here. This doesn't work very well. So for us, again, we don't have to deal with the three-dimensional aspect of all of this. It helps if we can envision, taking this thing right here and rotating it around the x-axis, making a circle, because that'll help us remember the formula when we use the disk method. But we don't even have to think of what the three-dimensional figure looks like.
Could you prove the circle volume doing this, like taking the integration of the top half and rotating it?
Yeah.
Okay.
Yeah. So we could go the disk method to prove the volume of a circle. We would just maybe take the top half of the circle, rotate it around the x-axis, right? That would generate a sphere. So we could certainly use this method to do that, yep. All right, I do want to denote here that with the disk method, the area, rather, the cross sections are circles. Let me say that. says find the volume using the disk method, this is what you're going to use all the time. In the same vein, we could take a region and rotate it around the y-axis too. So if we had something like this, rotate it around the y-axis. Remember, if this is the disk, our rectangles are perpendicular to our axis of revolution. So we could also do something like that. If you've looked ahead, you know where we're going with this, but the natural progression in, let's say, Calc 1 was to take an area like this that's butted up against one of the axes, X or Y, and find the area, right? So then we could have gone into this right here and say, well, now take this area that's against one of the axes, rotate it around the axis, and find the volume. Then we moved on to chapter 6.2, and we said, okay, well, now we have two functions rotated around the x-axis. So that's where we're going with all of this. We're going to look at, this is a very specific thing, just like area in chapter 5 was. And then we'll look at the more generic setting, like area was in 6.2. Okay, let's see how this works then. So we have the region bounded by our e to the negative x, y equals to 0, x equals to 0, and x equals ln 4. So that's our region. We're going to take that region and revolve it around the x-axis. We're going to revolve that around the x-axis. I'll specify on the exam which method to use. So we need to think of two things here. We're using the disk revolved around the x-axis. So two things we're thinking of. It's the disk method. It's parallel to the axis of revolution. Our rectangles are perpendicular to the axis of revolution. And we're thinking about disks as pi r squared or pi f of x squared. So really that's all we need, because that's the area. Area times thickness gives us volume.
So what about like what's displaced with the x-axis or the y-axis, whichever one you're revolving around?
Mhm.
So this would be like an inner green.
Yep, exactly.
Are we gonna get to that?
Yeah, we certainly will get to that. Because what you're talking about is, what we're talking about here rather, is a specific version of what you're talking about. So the version you're talking about is more all-encompassing than this one. So perpendicular to the axis of revolution, that our rectangles have a thickness, or our cross-sections have a thickness in the x direction. So this tells us just nature of the problem. We're forced to do this, so everything has to be in terms of x. Okay, so when you think about disk method or the other methods that we look at, think about the formula, what you're integrating, and then think about how do I draw my rectangle? Is it parallel or is it perpendicular? Those are really the two main things we've got to get straight. So everything's in terms of x. Since it's a disk, the volume is pi r squared. What's our radius here? So we're taking that and we're just revolving it around the x-axis. When we revolve that specific specific piece around, we generate that circle.
So the radius just be top minus 0?
Yeah, the radius is just the top minus 0, right? Because from here to here is the radius of that circle. Let me put that in a different color.
So then what? Would just be the
Right, because it varies, right? This radius is totally different than this radius. What it depends on is the y value, which is given by the function minus 0. So our radius is e to the negative x minus 0, or just e to the negative x.
So would your bounds just be L4?
Yeah, right. Is everyone okay with the radius being e to the negative x? Do y'all have any questions? So there's the area of our cross sections, pi r squared. Thickness gives us volume. We're just summing all of that up. X ranges from here, 0, to here, which is ln4. Are there any questions? Are y'all okay with the setup? Yeah.
How did you get natural log of 4 for ln4 for the top?
Oh, because we were given with the curve, e to the negative x is bound by x equals to 0, y equals to 0, and natural log of 4. So it's just given to us. Yeah, I mean, it's a good point though. Like, a lot of this stuff, you have so much information. You know, that's why, again, being organized is crucial, because some of this information can just easily fall off your radar. Okay, any other questions on that? So we're integrating e to the negative 2x with respect to x. What's the antiderivative of e to the negative 2x?
Negative 1/2 e to the negative 2x.
Right, right. So I'm going to go over here. So e to the negative 2x over negative 2, or negative 1/2 e to the negative 2x. Evaluated from 0 to ln4. So then the negative 1/2 is a constant. You can keep it in if you want. I'm gonna pull it out and deal with it later. So there's our negative 1/2 times our other constant pi. E to the negative 2x then, evaluated from 0 to ln4. So plug that in, minus pi over 2. ln4 goes in, so we have e negative 2 ln4 minus e to the 0. So let's just say we wanted this as an exact value. What is the exact value of e to the negative 2 ln4? Yeah, how'd you get 1/16?
Well, for e raised to the natural log of something is just that something.
Okay.
And 4 to the negative 2 is 1/16.
All right, good. Yeah. So you got to remember properties. You got to remember properties of logarithms and inverse properties of logarithms and exponents, right? So e to the negative 2 ln 4, if we just look at negative 2 ln 4, properties of logarithm says that number that's multiplying the logarithm can come out front or it's on this power of this number, right? And so e to the ln of anything is just that thing. So this is for the negative 2, which is 1 over 4 squared, which is 1/16. All right, so there we go. 1/16 minus 1. So we have 1/16 minus 16/16 negative 15/16 times the negative pi over 2. We have 15 pi over 32.
So if we did, like, didn't do the 1/16 and we put it in decimal, and then times it by pi, is that okay?
It depends on what the instructions are. If it says exact value, then no. If it just says find the volume, then yes.
Okay.
So if it says exact, it's got to be exact. There can't be decimals in it.
Okay.
Yeah. Oh, this one? Yeah. I'll finish this out. This is 2 over 4 to the negative 2. Yeah, just be mindful of the instructions. If if you write it as a decimal, it's not going to look pretty either. So, you want things to look pretty, or numbers to look pretty. All right. Well, as far as the work goes, I think hopefully we're okay with that. Just again, be super mindful of the setup, because as we go through 6.4, it's going to change. As we move to a more generic method, the setup changes slightly as well. So, just if you get hung up on something, please ask. That's a good place to stop. We'll take a break and then we'll continue 6.3. All right. So another example here where we're revolving it around the y-axis. And if you can draw a picture of these things, if a picture is not provided, I would recommend a picture so you can get your bearings on what's what. So we have the region bound by x equals root 25 minus y squared and x equals to 0. Use the disk method. So we're thinking pi r squared for the area to find the volume of the solid generated when it's revolved around the y-axis. Disks are perpendicular to the axis of revolution. So do we remember what that function looks like? Yeah, right. So that's x squared plus y squared equals 25. Circle radius 5. So we would have the entire circle, but we're looking at the region bound by that curve and x equals to 0. Maybe I should have said x equals to 0 and y equals to 0. I don't know what I should have said. Let me see if I have the shape in here. I'll just try to draw it. So which part of the circle is that? Okay, yeah, so be careful. This is when x is positive. So we have only the right half of the circle, the line x equals to 0. So we're taking that region, revolving it around the y-axis, and computing the volume of the solid generated when we revolve around the y-axis. So what are we going to generate when we do that? A sphere, yeah. So that's going to give us a sphere. So radius 5. Okay, since we're using disks around the y-axis, our disks are perpendicular to the axis of revolution. So here's, let's say, one of those rectangles. Consequently, that's also the radius of the circle that's generated when we revolve that around. So here's. So would we go, well, rectangles are our y's. They're all ranging from here to here. So it's from -5 to 5.
You also do the symmetry, you say it's 2 pi times 0 equals 0 pi.
Yep. Yep. So what is the length of that radius?
It's kind of a random question. Why are we doing the full, or just I guess the half sphere when it's bound by the x-axis?
Well, so because if we just had this, right? There is nothing bound by just that, because we have all of this. So it's ambiguous. We have to have a stopping point, I guess. So the radius element running this way, horizontal element, it's the right minus the left. So it's function minus 0. Is that function how we need it to be? 25 minus y squared? Yeah, because our rectangles are running horizontally, which means they have a thickness in the y direction. So this is also telling us that, you know, this is our rectangle, thickness dy. So that's good as it is. We don't need to resolve that for y. So our volume is pi r squared dy. Like we said, our bounds on y originally, if we set it up, go from -5 to +5. Basically the setup, utilize symmetry if you want to, but are we all okay with that? Yeah.
Where did 5?
Which one? This one or both of them? So this equation right here we're given, if we solve or rearrange that rather, we square both sides, and then we'll add y to both sides. So that's our circle centered at the origin with a radius of 5. So that's how we're getting those in points. Or, as we mentioned, we can compute twice from 0 to +5. Either way. Okay. So we have our constants 2 pi. Let's write this 0 to 5. And the roots undoes the square. The square undoes the root, rather. So this is just, we're integrating 25 minus y squared with respect to y. Everybody okay with that? Just a very similar, we saw a very, very similar example just previous to this. 25y minus y cubed over 3 from 0 to 5. So we've got 500 pi over 3. 500 pi over 3. Once we recognize, hey, this is my figure, I'm revolving it around the y-axis, it generates a sphere, naturally, the easier way to compute that volume is to just plug that into the volume of a sphere formula. So let's just kind of verify that check. Volume 4/3 pi times the radius cubed. And we can verify that that is also 500 pi over 3. So I guess this is the easy way, without integration anyways. Does that seem doable? Are there any questions? Second method, it's a more general version of the disk method. So remember, this setting here with our region in green, that's the setting we were in 6.2. So we moved to finding areas of more general regions like this. But now we're going to take a region like this and revolve it around, let's say, the x-axis or the y-axis or whatever. When we take this, now just notice the difference. It's not sitting against an axis of revolution anymore. That's the only difference here. But it does change the cross sections when we revolve this. So when we revolve that, we see that it's no longer a disk. It's, I guess, what your book's referring to as a washer. And then we do the same thing. We slice and we sum up the volume of all of those washers. And so we get something like that with our holder. Looking at those kinds of things.
Would this ultimately just be pi times f of x minus g of x all squared?
Well, we wouldn't square f of x minus g of x as a quantity.
Square
Individually, yeah. So let's call the distance from the center to the outer edge. Let's call that capital R, and from the center to the smaller square, lowercase r. Just so we can see where that formula comes from. So we're finding the area of the cross section, which is this washer here. So this is the area we're looking at. We're looking at that area. And if we go back up to the figure, the top portion, this is our, first of all, can everyone see, or is everyone convinced that the axis of revolution is the center of that washer? Because we take this region and we revolve it around that thing right there. That's going to be the center. Okay, so this is from here all the way down to the axis of revolution. That's our capital R. And then from here to the axis of revolution is our lowercase r. So really the big radius, or the outer radius, is generated by the top function to the axis of revolution, that distance. And the inner radius, or the smaller radius, is generated by the function closer to the axis of revolution. So to find this area, we would take the area of the entire circle, and that's pi times capital R squared. Then we have to subtract out the area of the smaller circle. And then we'll just factor that pi out. So we have the area of that cross-section is pi times the quantity capital R squared minus lowercase r squared. But again, the radii are determined by the function itself. They vary throughout the figure, or throughout the region. I think I have that down here. All right, well, I accidentally didn't put that in there, but what we're doing here, we're saying that the volume from A to B is pi times, we'll keep it consistent with how the figure is set up here in this first green region. So the capital R would correspond to which function? Yeah, the top. So here's, whatever this distance is, this is from here to your axis of revolution, that's capital R. Again, we're just measuring that distance. That's f of x minus g, the bottom, which is 0. So that's just f of x squared minus our small radius corresponding to this right here, the distance from here to here. Again, top minus bottom, g of x minus 0. So that radius squared. So for this to become the disk method, what has to happen?
Multiply by pi and square.
Well, so we do have the pi and the square, right?
We would only have one function, and it would only just be f of x, which is the disk, right?
Right. So if it's the disk method, then the function g of x is 0. It is one of the axes, right? If g of x is equal to 0, because if g of x is 0, then that's pi times f of x squared, or just pi r squared, because this is all gone. So the disk method is, in fact, a special case of this particular method, the washer method. Or in terms of y, let's say c to d. The one that's positive that goes first, we're squaring, is just the longer of the distances from whichever function to the axis of the revolution. And the second one that's negative is the shorter of the two. Again, maybe think about this as large radius, small radius, outside radius, inside radius, however you want to keep track of that, whatever makes sense to you. Have any questions on this initially? So our region bound by y equals x, x plus 2, x equals 0, and x equals to 4. There's y equals to x, x plus 2. Just set it up here. There's 2. say this is 4 right here. I mean, really, it's the line here, but. So we've got, there's our region. Washer, again, tells us what method washer. We're thinking pi f squared minus g squared, maybe. Or outer squared minus inner squared. Washer, volume of the solid generated when it's revolved about the x-axis. Again, these washers are just general disks, right? So these things are still, disk washer are still both constructed perpendicular to the axis of revolution. Revolved around the x-axis. So our washers, or sorry, our rectangles need to be perpendicular to that axis of revolution. So we've not only reminded ourselves of the formula, but now we have this picture to construct it so we know what variable we're using, what bounds we're using, etc. So this is some thickness. Let's just exaggerate this rectangle. Thickness dx. All functions y equal to, which they are. So take a few minutes, set this up according to the formula. Don't try to simplify it or evaluate it. I just want to see if we can all set this up. Anybody want to volunteer? What you got?
48.5.
Okay, that's the answer. What'd you get for the setup?
Let's see, that's 0 to 4 and 4x plus 4x.
Okay, before that, what's your outer radius
Oh.
squared minus your inner radius squared?
Plus 2 squared minus x squared.
X plus 2 squared minus x squared?
Yes.
Yeah, thank you. Appreciate it. What do y'all think? Does that look all right? So here's our outer radius. Keeping in mind, again, we're rotating it around the x-axis. Our outer radius is the longest distance for the top function to the axis of revolution. So again, that distance is measured by the function minus 0. That function is x plus 2 minus 0. We're squaring that. And then the short radius here, or the inner radius, is given again by the bottom function minus 0, which is x minus 0 squared, which is just x squared. Is that all right? Everybody okay with that? Okay. So then we just expand, combine, simplify, etc. X squared plus 4x plus 4 minus x squared, so we have just 4x plus 4 dx. And then I think that's pretty straightforward from there, 48 pi. I hope anyways. Do y'all have any questions? Okay, let's try number 6. It's kind of similar, but a little different. got that far. Did anybody get the setup and feel confident sharing with us? Or do you need more time?
I'm not confident, but I'll try.
All right.
I think it's volume equals, yeah, and then pi, and then in brackets, y squared minus y squared over 4.
Let's do green this time.
And then y.
Okay. And then your bounds.
6 on the top,
Okay.
maybe 0 on the bottom.
Maybe 0 on the bottom. All right. What do y'all think about that setup? Okay. So here we have. Since our rectangles are perpendicular to the axis of revolution, which is the y-axis, we've got everything in terms of y. Okay, because our rectangles have thickness in the y direction. Okay. So we have this weird little triangle revolved around the y-axis. So remember the distance from the axis of revolution to the function furthest away, that's your outer radius. So our outer radius, we just need to measure that length, right minus left. The right function is given by this one here, which is y equal x. So y minus 0 is that length. So that length is y minus 0. That's the radius. So y minus 0 squared. The inner radius from the axis of revolution to the function closest to. So that's our small radius, if you will. Again, distance right minus left. That function is y equals to 2x, but we needed x equal. So this function here, y equals to 2x, is y over 2 equals to x. So that's our radius, y over 2. Inner radius squared, y over 2 squared. These rectangles that are filling this region up go from here all the way to here, which is y equals 6. So our bounds should be from 0 to 6. Are there any questions on that setup?
This really lets you find the volume of some really weird shapes.
Yeah, it does. What I always thought was weird is like especially through the calc sequence and even like in differential, you spend so much time studying functions. But if this were like a shape in real life, how would you even begin to determine that that's 2x and that's x, right? How would we know this curve right here is like a part of a sine curve, right? So like in calculus or differential, you're always given a function. But in the real world, like, is that clock really a perfect circle? Or is it an ellipse? You know, how would we actually start out with some function? That was always my question. Because you're not given a function in the real world. You don't know the function that describes the shape of that tulip. Yeah.
Well, yeah, because you have to make it yourself.
Right.
You go take measurements and try to approximate it.
Yeah.
Complex things.
That's how, and that's where computers like greatly aid us. We take some measurements, put it in the computer. Computer models best fit. Boom, there you go. There's your function. Computer basically does everything else too. All right, setup. Integrating shouldn't be terribly hard. We just have two similar terms there. You should come up to 54 pi. 54 pi for that.
You
Okay.
go
Backwards.
the volume and determine the bounds that are containing that volume.
The bounds that are.
I don't know, so
Right.
that volume,
Uh-huh.
I don't think there's a way to do it. I can't.
No, because honestly, there could be like infinitely many three-dimensional shapes that could have that equivalent volume.
Yeah.
And some of them could be like totally weird. Like like an octopus can have that volume. How would you know what I mean? But yeah, it's good to think about, going back and forth for sure. I like where your head's at. Yeah, too many options. All right, last one. So we've got a region bound by absolute value of x, 2 minus x squared rather. Use the Washer method. So Washer method, we're thinking about pi times f squared minus g squared. Volume generated when r is revolved around the x-axis. So we have our absolute value. Try to get this right. Yeah, close enough. So absolute value, and we have our function 2 minus x squared. So let's just say this is 2 right here minus x squared. I did okay. So the region bound by those two curves is this ice cream cone in the middle, or the snow cone. So I'm going to erase some of this. So one of the things that we're dealing with an issue, not really an issue, but we are dealing with the absolute value of the function. So just like when we were talking about distance traveled versus displacement, we didn't actually end up dealing with the absolute value of that particular function. We said, right, some regions are positive and some regions are negative. The regions that were negative, we just put a negative in front of. So it's the same idea here. This function is really this function. So depending on what side of the y-axis we have two different functions we're looking at. That really is the absolute value function. So that's one of the key ways to kind of break this problem apart. I didn't draw it as perfectly as it is, but is there symmetry with respect to the y-axis?
Yes.
Okay, so with the symmetry in mind, instead of taking this entire thing and rotating it around, let's just look at this half and revolve it around, because that's going to achieve the same effect as if we took the whole thing. Just like whether you take a whole circle or half circle and revolve it, right, you still get a sphere. Whether we take this whole snow cone and revolve it, or just half of it and revolve it, you're still getting the same figure from that. Do y'all agree?
Yeah.
Can you see that in your mind? So let's just make that note before we proceed. Use symmetry. We're going to find the volume, or set up the area rather. Washer method revolved around the x-axis. Washers are perpendicular to the axis of revolution. So top minus bottom, that kind of thing. dx, thickness dx. Everything's in terms of x for us. So we're using symmetry, meaning we're going to go from 0 to this intersection point, and then we'll just double everything. So what is that intersection point? What is this x value right here? Yeah. So I just say we'll double that from 0 to whatever. But we have, where does the quadratic meet the absolute value? Again, we don't need to use the absolute value because we know that that x value is positive. So since that x value is positive, there's no need for this. So when does 2 minus x squared equal to x? It's just a quadratic. It factors very easily. You'll come up with two answers, x equals to 1 and negative 2. Since we're talking about this point of intersection, that negative 2 doesn't even make sense. So this is an x value of 1 here where it intersects. So this is an x value of 1. If we wanted to find the other point of intersection, we would say, when does the quadratic equal negative x? Because that's a line negative x for negative values. But it's symmetric, so we would expect that other value to be negative 1. All right, so based on what we have here, revolving this region around the x-axis, what does that setup look like for the volume? Does everybody have that? We'll have pi integral from 0 to 1. Is that right? Okay, yeah, 2 pi, because we're going to double that region from 0 to 1. So there's our pi. What's our outer radius? Right. 2 minus x squared. That's our outer radius. We have to square that, so don't forget to square that. That is this distance from here to the axis of revolution. Okay. So we have outer radius minus, what's our inner radius? X. Inner radius is x. Don't forget to square that. So let me mark this out here. That's our small radius. Top minus bottom, x minus 0 squared. That's going to make it a whole lot easier if we wanted to utilize the entire region to find that volume. Then again, we have to integrate two separate pieces, because on the left side you have a negative x as that function, and on the right side you have a positive x. So if we didn't utilize symmetry, then it's pi times the integral from negative 1 to 0, 2 minus x squared minus the minus x squared, right? Plus the area from 0 to 1 of what we have here, 2 minus x squared minus x squared dx.
Still the
Same answer, same volume, but utilizing symmetry is much easier, right? You just get that as opposed to that. We'll just say that this is without symmetry. All right, so the setup, most crucial thing. Of course, there's room for error when you're integrating these types of things, but is everybody okay with the setup? Same idea, expand, combine like terms. You're going to have what they call it, a quartic function, x to the 4th. Still a polynomial to integrate. 76 pi over 15. Exact answer. It's basically 6-3. Do y'all have any questions at all on that? So start the homework if you can. Let me know if you have any issues. I'll be happy to look at homework questions at the beginning of class if you have any. So try to do those things without the help either. Certainly do that in class. The summary is the last page. So I do just remember that the disk and washer are perpendicular to the axis of revolution. Here we're revolving it around X. So if you want to look at that, and maybe you can kind of get all of this stuff straight in your mind so you don't have to think about, okay, well, dx rotating around this. Maybe you can put it all together more seamlessly if you look at it. But I just want to point that out, perpendicular to the axis of revolution. Next time in 6-4, we'll look at what happens when we have a rectangle revolved that's parallel to the axis of revolution. So that's 6-4. I guess we can go. I would hate to, in the last couple of minutes, start a new section. If we do get behind, we can make up time in 6-6, 6-5, and 7-3. All three sections are pretty short, to be honest. So if we do get behind, we can make that time up. I do owe y'all 3 minutes anyway, so. See ya.